Hello everyone, this is Ostroumov, and today we will continue our talking about modern navigation equipment, and especially today I would like to discuss with you the basic principles of cooperative navigation equipment. As you know, nowadays we have a lot of application of cooperative navigation. We can meet it in different light shows when a fleet of UAVs are used to perform some visual effects, and this is amazing. And also we can meet cooperative navigation approaches in robotics when multiple robotic vehicles perform some particular tasks. Of course, in some cases, swarm technologies and methods can be used in cooperative navigation. That's why today cooperative navigation is one of the highly discussed topic in modern navigation application. In most cases, cooperative navigation grounds on using multiple vehicles which can move in space. And also we use some data, for example, distances or angles about this formation. And based on this data, we can perform navigation. What does it mean? It means that if we can measure distances within vehicles in some colony or formation movement, we can calculate coordinates of each vehicle in our colony. And it can be done by cooperative navigation principles and the same technology. Okay, let's consider some example, maybe. All vehicles in cooperative operation are equipped with a digital data link to provide surveillance and task coordination. Communication modules from a network for digital data transfer between vehicles. Most of the currently used equipment for digital data transfer includes range measuring between receiver and transmitter by different methods, and in this case the most useful it is a method based on losses of energy during the radio waves propagation. That's why if we can measure power level of received signal, which we usually got in modern software defined radio, then we can count distance to the object or distance to the transmitter. And then this range data may be useful for improving the navigation performance of the whole formation movement. As an example, if we consider a case with cars, if we have, for example, 4 cars, and on board of each car we have some automatic car control system, and let's think that on board of each car we have communication equipment like 4G or 5G or with the help of some other technologies. Actually now it doesn't matter. And based on this wireless communication technology, we can measure the power of all other transmitters in our formation. of vehicles. And it makes possible to count distances to these transmitters or distances to these vehicles. That's why quite easy we can get distances from one car to all other cars in the road. That's why if we have a colony of cars, okay, and each car know distance to all other cars in our colony, with the help of this information we can estimate coordinates of each car in our like network of cars. If we consider about modern technology, first of all we can start from the easiest level, and it is Bluetooth. That's why we can use a mobile phone with a Bluetooth module, and then we can use specific software to measure power of each Bluetooth transmitter within like 30 meters. That's why we can use a simple Bluetooth receiver to get ranges to all other Bluetooth transmitters in the short range, like 30 meters. However, for road traffic, 30 meters will be enough. For such case, if we consider like quite congested traffic. Okay, let's go next. And in this case, our cars or vehicles we can represent in form of network, where each vehicle is a node, and measured range to other vehicles it is edges. That's why we can represent this data in form of graph with a help of some agency matrix weighted by distances or ranges by measured by Bluetooth equipment on board of car. Then we've got measured distances, and the task is how we can estimate coordinates of each vehicle information based on knowing only ranges between cars information. And in this case we can use quite simple equation based on formula for range between 2 points. That's why for two-dimensional space it looks like that. R is equal squared difference between coordinates and sum by coordinates. Okay, that's why by this quite easy formula we can estimate range. That's why we can use this equation and make a system of equation by known ranges and unknown coordinates of vehicle location. For case of three-dimensional space, we need to take into account the axis. And of course, we are talking about Cartesian reference frame. In case of solving system of this equation, we need to apply some methods, because this system of equation is not linear. That's why we usually apply some methods to make this system of equation linear, and then we solve this system of equation with the help of solving linear equations. That's why there are different ways how we can linearize these equations. However, the two most common of them, it is just minus some equation from another equation and then open these brackets. It gives us minimization of equation, and then we can reduced power level in this case, and our equation becomes linear. Another case, it is usual using Taylor series expansion. That's why we can represent this equation in Taylor series expansion, and then just form particular matrices to solve our linear equation. After linearization by any method, our system of equation can be represented as following. That's why D here will be some matrix with ranges, then A, it is like a coefficient matrix, and X with this matrix of unknown coordinates of each vehicle. Then we can use weighted least square method to solve this system of equation and get in coordinates x. Why we need to use weighted method? Because each range is measured with errors or with some noise. That's why to minimize noise activity or influence in our total result, we need to use only weighted least square method. And as a result, we've got coordinates of our vehicles x, y, and z if it is three-dimensional plane, and also we can quite easily estimate errors of positioning in horizontal, in vertical, and in three-dimensional space. Next, quite important to talk about what is the perils of cooperative navigation. A number of unknown variables in navigation equation put strict requirements on the amount of input data. Number of input ranges between nodes should be not less than a particular number of vehicles minus 1, because coordinates of one reference point should be known in a priori. If we don't know location of any vehicle, we locate our reference frame at the center of our vehicle formation. That's why a coordinate of one vehicle can be associated with the reference point of our coordinate system. And it means that in this case, coordinate of this vehicle will be equal 0, 0, 0. Okay, that's why in any case we make assumption about known coordinates of one vehicle. If we don't know it, we just make it equal to 0. And it means that it will be reference point of our local reference frame for vehicle formation. And in this case, perils for known nodes and to known number of ages or measured number of ages, we have as following. For two-dimensional space, we've got this formula, and for three-dimensional space, it's like this one. And a maximum number of variable ranges from n node can be estimated by combination by 2. That's why this is simple combinatorics to get maximum number of ages available in particular network. That's why just number of combination by 2. Horizontal navigation is possible with a fleet of vehicles of more than 4. In the case of 4 vehicles, all ranges between them have to be measured or be known. Navigation in three-dimensional space is supported with more than 6 vehicles. Also, in the case of 6 vehicles, all 15 edges have to be measured. Many years ago, I have counted such kind of table, which represents perils for solving cooperation navigation equation. And here we have one column. It is number of vehicles, and then we have perils for number of edges. That's why for case of 2 vehicles or 3 vehicles, two-dimensional navigation is not supported, as well as three-dimensional navigation. If we have 4 vehicles, we need to measure all edges or all ranges, which is 6. If we have 5 vehicles, total number of edges in the network of 5 nodes is 10. However, for localization of cooperative navigation, we need at least 8. That's why we need to get at least 8 edges up to 10 edges. In case of 6 vehicles, using in-vehicle formation movement, the maximum number of measured edges is 15. However, for solving navigation equation, we need just 10. That's why from 10 to 15 measured distances, we need to know to count coordinates of each vehicle in our formation relative to some reference frame which we think that is located and in coordinates of 0, 0. And also in case of 6 vehicle colony, okay, three-dimensional navigation is possible. And we need to know all 15 edges or all ranges between any vehicle in the network to count 3 coordinates, x, y, and z. And then the same situation for 7, 10, 20, and also here you can find results for 100 vehicles and for 150. And here we have also important results that, for example, for 100 vehicles, the total number of edges is approximately 5,000. However, for solving navigation equation, we need at least 198. That's why we can see that if we have a big amount of ranges in our network measured or known, then we do not need to know all the edges in the network. We can use just a small amount of them, and it will be enough to count coordinates of each vehicle in our formation. However, for three-dimensional navigation, we need at least for 100 vehicles, for 100 edges more to be known to solve this equation in three-dimensional space. If we can represent this data in graphical form, we can get a specific area of perils which indicate how many edges or measurements we need to get our coordinates. That's why here's number of vehicles or number of nodes, and here number of ranges. The blue line, it is total number of combinations. It means we have all ranges between all nodes in the network. And the green area shows solution of these navigation equations for two-dimensional space, and the red one for three-dimensional space. That's why for three-dimensional space we always need a little bit more data, because we get extra number of unknown variables. Solution of navigation equation gives coordinates in a local coordinate system with a reference point at the selected vehicle. It means that the local coordinate system may be rotated from global at a particular angle. Thus, a solution with only one reference frame gives us geometry, but rotated at some particular value of angle. Rotation of one reference frame within another at angle, for example, alpha, can be done by the following transformation equation for case of two-dimensional space. That's why here we've got global reference frame. This is rotation matrix, and this is x is coordinates in local reference frame rotated in an angle alpha. Thus, the second reference point can be used to fix vehicle graph in a space. In this case, measuring of coordinates of any 2 points in the graph is required. Let's see some example. Cooperative navigation method is used to solve a graph of road traffic. This task is actual in the case of using modern data transferring equipment between all road traffic participants. And in this case, we use just computer simulation. That's why we take a photo based on some UAV equipment, and then we use specific algorithms to detect location of cars in the road. Due to known location of UAV, we have algorithms which can make to measure coordinates of each vehicle in latitude and longitude. That's why we use UAV with specific camera which can tune optics, and then we use the data of UAV location and the optics performance to count latitude and longitude of each point on this picture. And we count latitude and longitude of each vehicle, and then we simulate measurements of ranges between all of these vehicles based on simple path loss model for free space propagation case. And here you can see the red circle. It is coordinates of vehicle location which we've got after the getting configuration of our formation vehicles. Then we apply our formulas. That's why we've got 15 ranges between our nodes. And we use vehicle A as a reference point for our reference frame. That's why at vehicle A we've got 0, 0 coordinates of our local reference frame. And we can see that we've got solution of navigation equation. It was green stars. And you can see that we get correct relation between these stars. However, this configuration is rotated with the center of our reference frame. That's why we need to count angle alpha and then apply rotation of our results to this particular alpha angle. And after the rotation, we've got rotated results. It is blue star, and we can see that mostly it coincides with the circle. Because we simulate errors, that's why we have some distribution or deviation from centers of true vehicle's location. That's why quite important that if we talk about formation movement and if we need to know coordinates of each vehicle in formation, we need to know at least coordinates of two vehicles. What does it mean? It means that on board of only two vehicles in formation have to be some positioning system like GNSS receiver. And in case of cars, we need to measure coordinates of two vehicles. And then by known ranges, we can count coordinates, latitude and longitude of each vehicle in our formation. Also, it is important that this problem we need to solve in Cartesian reference frame. That's why we transform our latitude, longitude, altitude from their LLR to their ECF and then to the local frame. However, if you've got ranges, that's why we can miss transformation to the local frame. We can use ECF. However, it depends on what kind of data we have. And this is the main idea of cooperative navigation. It means that by known ranges inside of formation movement, we can get coordinates of each vehicle in our formation. Okay, thank you. That's all that I would like to share with you. Thank you for watching. If you have questions, I will be glad to answer. Thank you. See you later.